Attention is the main component of transformer networks. Attention has three main parts: queries, keys, and values. Think of it this way. Queries are like asking questions. Keys are like possible answers to those questions. And the model wants to decide how well each answer aligns with the question. This alignment is measured using the dot product between the query and the key. Once we measure this agreement, we apply softmax. Softmax smooths the agreement scores and turns them into weights. Then we multiply these weights by the values. So conceptually, you ask a question, you evaluate the possible answers, and then you weight the information you receive. That is the core idea of attention. As a result, attention becomes a very powerful communication mechanism between tokens. But there is a problem. The attention mechanism itself does not care about the order of the inputs. If you look at the math, attention behaves like a set operation. So in order to introduce sequence information, we add positional encoding. In the original transformer paper, the authors propose using a mixture of sinusoidal functions with different frequencies to encode position. Modern transformer networks often use more advanced methods such as rotary positional embeddings or ROP, but the original sinusoidal encoding was the first solution. Once we add positional information, we can properly perform attention over sequences. Now another important point. According to the original paper, after the attention computation, we apply normalization. But attention itself is not doing any real thinking. Attention is only a communication mechanism. The real computation happens inside the feed-forward network. In fact, in most transformer models, the feed-forward layers contain the majority of the parameters. After that, we add residual connections very similar to what was introduced in ResNet to improve gradient flow and training stability. This entire structure is what we call an attention block. We then stack many of these blocks on top of each other. And finally, attention is not just single attention, it is multi-head attention. This means the model can ask multiple different types of questions in parallel about the same sequence and capture different relationships at the same time. When we stack many of these multi-head attention blocks, we obtain the transformer network.